Welcome back, everyone. We're going to do a little bit more on energy and the relationship between potential energy and forces. Um, and then we'll do some more examples. And we're going to go back and do at least one Newton's law forces kind of examples, and then we'll do some more energy examples as well. All right. But to begin with, let me just go back to this definition of potential energy as minus the integral from some initial position to some final position of the component of force along some path. And that integral is essentially equivalent. We could write it in terms of an indefinite integral as minus the antiderivative of this quantity of f dot dx along some path plus some arbitrary constant. The arbitrary constant essentially being related to your definition of whatever the 0 point of potential energy that you chose is. But the fact that we can write it as this antiderivative means that we could also take the derivative of both sides of that middle equation and recover the integrand, basically the f of x. In other words, that the force along a particular direction is minus the derivative of the potential energy in that same direction, or with respect to that same direction. We could write this in 3 dimensions, and here we introduce a new notation, a new symbol, this upside down triangle, which gets called the gradient operator. And so we say that the 3-dimensional force vector f, which is a function of position r, is minus the gradient of the potential energy. And what that upside down triangle means is what this next one says. It basically says that you take the the derivative of u with respect to x and multiply that by the x position, or the x unit vector, and you do the same for the y, or the derivative of u with respect to y and multiply that by the y position, the y unit vector, and the same for z multiplied by the z unit vector. Don't worry too much about this particular formalism. We're not going to rely on it in this course, but it is something you will see quite a bit more as you go forward, particularly those of you who go on to Physics 2 will definitely run into the gradient operator again, and this notion of the relationship between force and potentials, or potential energy. And while this is basically just a rewriting, it's just another rejiggering of the math, it means something conceptually different, because we've moved from the idea of a sort of the energy being a state of the system, to here the energy becoming, or the potential has become a field. What does a field mean? Well, a field is a mathematical construct which basically says that every position in space has a certain value associated with it, and that value is the potential for that position in this case. So for instance, if we go back to gravitational potential energy, if we turned this into a gravitational potential energy field, or a gravitational field, what this means is that at this location there is less gravitational potential energy, and as we go up there's more and more and more gravitational potential energy. That this pen sits in a field of energy, in an energy field where the strength of the potential energy increases the farther away from the surface of the planet I get. The closer I am to the surface of the planet, the closer I am to lower down, the less the local gravitational potential energy field is. And as we increase, the gravitational potential energy field is increasing. And in this way of looking at it, then the force becomes the derivative. It becomes the rate of change of that field with respect to position, right? So the faster your force, or the faster your energy field is changing, the faster the potential energy of your force is changing, the larger the force. And this also means that if you come to a place where the potential energy isn't changing as a function of position, then you've reached a place where there is zero force, that places with zero force, places where your object will be in equilibrium, those will be places where at least locally you're in a local minimum or maximum of the potential. Let's go back to this first statement here and just look at it slightly in a more familiar context. Let's be concrete about what we're talking about. So let's talk about Galileo's gravitational potential energy. All right, so the gravitational potential energy we've been using is the one where we say that the potential energy is m times g times some height, or in this case y. And if we just use this this definition here of f of x, or f of y in this case, we say f of y is equal to minus du dy in this case. Well, du dy minus is equal to, this is equal to minus d by dy, the derivative of mgy. And the mg comes out, because those are constants, so minus mass times gravitational acceleration constant times dy dy, and dy dy is obviously just 1. And so in other words, what we're left with is that the gravitation, or the force in the y direction due to this gravitational potential would be minus mg, which is the result we should be expecting, that indeed the force of gravity has a magnitude mg, and in this case it's in the minus y direction. So we've recovered something familiar. Good, great. Well, let's take a look at this idea a little bit further and make a plot here with y as the independent variable, and on the vertical axis here we're going to put energy. And if we take the gravitational potential energy and plot it in here, well, this as a function of y, is mg times y. Well, that's a slope times our independent variable. In other words, this equation is the slope of a line that goes through 0, or this equation is the equation of a line that goes through 0, has slope mg. So we could call this u as a function of position y. And if we're right here at some position, say y prime, then this height here, this would be the gravitational potential energy at that y prime, just mgy. So this height here is gravitational potential energy at y prime. And if we had a total mechanical energy up here, E total, then what we could say is, well, obviously if this is the gravitational potential energy, and there aren't any other potential energies involved, and this is our total energy, then this distance here, that must be our kinetic energy at that same position y prime. And you can see the closer we get up here, this point up here, that's y max. That's the highest any object with total energy E total could get to, and the kinetic energy at that point would be zero. All of that energy would be in the form of gravitational potential energy. And down here on the ground, all of that energy is in the form of kinetic energy. And somewhere in the middle, we have a mixture of kinetic energy and gravitational energy, but they always add up to the same value. And so this is a way of thinking about these potentials, these potential energies in a slightly different context, from a slightly different point of view. All right, well, let's move on now and do some more examples. And this first example I want to do is actually a Newton's laws forces kind of problem. But it illustrates an aspect of those that I think I wanted to emphasize a little bit more. We didn't quite go too much into detail in class with these. We did do some examples of these kinds of problems, but I wanted to look at this one because this one introduces a wrinkle that I don't think we talked about explicitly in class. We mentioned it a couple of times, but we never actually did a problem that required us using this. So let's go ahead and take a look at it. It says, a designer wants to display a 200 kilogram piano on a ramp rising 30 degrees above the floor of a piano showroom. She secures the piano by attaching it to a cable running to the top of the ramp over a frictionless pulley and down to a second frictionless pulley held down by a 180 kilogram counterbalancing weight and up to an anchor in the ceiling. A second cable runs from the counterweight to the floor. And it asks us to calculate the tension in each cable, and then also if the cable between the floor and the counterbalance breaks, how fast will the piano accelerate? So let's start with the first of these, and then we'll look at the second one as well. All right, so we can begin here. We have a diagram, but let's go ahead and make a free body diagram here, and we'll do actually two of them. One for the piano here, and then we'll also have to do one for the other potentially moving object, which is our counterbalance. All right, so the forces acting on our piano, well, there's a weight, gravitational force of the piano pushing straight downward. There is a normal force acting perpendicular to the surface between the piano and the ramp, and there's a tension force which is pulling upward along the ramp. And so in this particular case, it might make sense to adopt a coordinate system which is aligned with the ramp, because two of our force vectors are already lined up with that coordinate system. So let's go ahead and adopt a parallel and perpendicular coordinates, and our perpendicular coordinates are this one, and our parallel coordinates are this one. And I've drawn the positive parallel direction sort of down the ramp, because that's the direction I would expect the piano to roll naturally if it was going to go somewhere. And that'll help us sort of not have to deal with extra sets of negatives running around at some other time. So in this coordinate system, then we need to break up our gravitational weight into parallel and perpendicular components. And I'm going to go ahead and draw that over here. So again, this is our weight. And there will be a component of our weight going down and a component of our weight trying to go across. And so we'll call this the parallel component of weight. That's going to be, here's our 30-degree angle. I'll just label it as theta there. So this is going to be mg times, this is the adjacent, so that's going to be cosine theta, and this one is going to be mg sine theta. And so we can set up our perpendicular components of force are going to look like this. We have in the positive perpendicular direction our normal force, in the negative perpendicular direction minus mg cosine of theta. And we're not expecting or desiring our piano to accelerate in the perpendicular direction, so that's got to be 0. And this would tell us that the normal force is equal to the mass of the piano times gravity times the cosine of that 30-degree angle. But in this case, we don't actually care too much about the normal force. So we calculated this. It doesn't really tell us much. The parallel components of force, well, in the positive parallel direction, we have mg sine of 30 degrees. And in the negative direction, we have tension. And if our piano is to actually sit stably on the ramp, then it too must not be accelerating in the parallel direction. And so our force balance equation equals 0. And then this we can say the tension is rather directly mg sine of 30 degrees. And plug in our mass here is a 200 kilogram piano. Our gravity here is 9.8 meters per second squared, and times the sine of 30 degrees. So 200 kilograms times 9.8 meters per second squared times the sine of 30 degrees is 980 newtons. All right, we didn't even have to discuss the counterweight to discover that the tension was 980 newtons. This is the tension, however, in the rope on the piano. So we're going to label that tension 1. tension 1, tension 1, and tension 1. Because there is this second cable here. Let me see if I can point at it. There it is, right down there. The one that's tying the counterweight to the floor. Right, see up here, each of the tensions coming off of that upward, or off of that pulley on the counterweight, both of those are pulling upward, and those are both the tension T1 that we just calculated. But this little bit of cable running from the bottom of the block to the floor, that's a different tension. And so to calculate this, we have to do a free body diagram of the counterweight. I'm going to go ahead and draw the pulley on the counterweight as part of it. And we have, as I said, two versions, or 2 times the upward tension force that's from the cable that's holding the piano going upward. We also have a downward tension force, a different tension, tension 2. Let me draw that a little bit clearer. That this here is tension 2 going downward, tying that block to the floor. And we also have the counterweight's mass and gravity also pulling it to the ground. And this counterweight is only going to move vertically, right? So we'd only have to worry about up and down motion. So I'm going to call this basically the plus y direction. And the sum of forces in the y direction, well, we're going to have 2 upward directed T1s minus a T2 minus mass of our counterweight times gravity. And again, if our system is remaining in equilibrium, then that also will equal 0. We already solved for T1. We know the mass of the counterweight here is 180 kilograms. So the only thing we don't know here is tension 2. So we can solve for tension 2. We would be bring it over to the right here. So 2T1 minus mass of the counterweight times gravity equals T2. And now we can just plug in some numbers. 2 times our 980 newtons minus 180 kilograms times 9.8 meters per second squared is equal to our tension 2. So 2 times 980, that's 1960 newtons minus 9.8 times 180 is 1764 newtons. And 60 minus 1764, 96 newtons is the tension in cable 2. So cable 2 doesn't have to have a lot of tension on it. In this case, that was the whole point of having a counterweight system, so that the weight of the counterweight here is supplying most of the force needed to counteract the weight of the piano, and it's just a little bit of imbalance that the cable itself has to overcome, this 196 newtons. All right, so then we can look at the second part of the problem, which asks, if the cable between the floor and the counterbalance breaks, how fast will the piano accelerate? All right, well, let's start with the counterbalance, and we'll look at that, and then we'll examine what happens with the piano. So now we go back to our free body diagram. right? And everything is the same except tension 2 has gone away. So we still have the mass of the counterweight times gravity going downwards. We still have two versions of a tension going upwards, but this tension is not necessarily the same as it was beforehand. When the tension of the little cable broke, the tension of the big cable can also change, and indeed probably will, because the system is going to start accelerating. All right, so the force balance equation here is going to be two upward directed tensions minus gravity is equal to the mass of the counterweight times the acceleration of the counterweight. And again, we expect the acceleration of the counterweight here to be upward because we needed that downward tension to keep the system in check. So without the downward tension, without the downward pull from that bottom cable, we expect that the counterweight is going to go up as the piano slides down. All right, so this is going to be one of our relevant equations to calculate how fast the piano accelerates. The other one we have to look at is go back over here to our free body diagram for the piano, right? Well, the free body diagram for the piano hasn't actually changed significantly. We still have gravity going downwards, a normal force going this way, and a tension force going that way. The value of the tension force may have changed, but nothing else has. And so our force balance equations, we're still going to keep that same perpendicular and parallel. But if we go back now, we still have a normal force. We still have the mpg cosine of 30 degrees in that direction. We have our mpg sine of 30 degrees in that direction, and we have our tension in that direction. Again, the same four forces that we had earlier, except that the value of this tension force has likely changed. The perpendicular components again aren't going to tell us anything interesting, so let's look at just the parallel components. In the plus parallel direction, we have the mass of the piano times gravity times the sine of 30 degrees minus just our tension T, but now that's going to equal the mass of the piano times the acceleration of the piano. And here is a second equation, right? And let's count up the unknowns. Well, tension, that's an unknown, okay? And the acceleration of the piano, that's an unknown. And the acceleration of the counterweight is an unknown. And let me explain why. Because the counterweight is not going to move at the same speed as the piano. All right, to understand why that is, we have to relate the motions of the counterweight to the motion of the piano. And this is the bit that I wanted to redo this problem for, because we didn't really work through one of these where we had to pay attention to the relative motion of two of these things in an Atwood's machine problem like this. So let me draw our system here. All right. So that's kind of what our system looks like. And the relationship that relates this to that, the really important relationship, is that the length of the rope doesn't change, right? So if we move the piano a distance d, right, then we have to move the rope a distance d, which means we have to shorten the total path that the rope takes over here by that same distance d. Well, to do that, we move the counterweight up, but the counterweight only has to move up half as much. It moves up by an amount d over 2, and then this distance from the ceiling to the weight is smaller by a factor of d over 2, but also the distance from this pulley to that pulley is also shortened by that same d over 2. Okay, what this means is that the distance that the counterweight only moves half the distance that the piano does, right? So the displacement of the piano is twice the displacement of the counterweight. That means that the velocity of the piano must also be twice the velocity of the counterweight at any particular moment in time, and that the acceleration, or the magnitude of the acceleration, must also be twice the magnitude of the acceleration of the counterweight. That the acceleration of the piano must be twice the rate of the acceleration of the counterweight. In both cases, we've adopted a coordinate system which is sort of a forward direction coordinate system, if we will, that the positive sense of motion at the counterweight is up, and the positive sense of motion at the piano is down the ramp. And so what we can say here to link those two together is that the acceleration of the piano is twice the acceleration of the counterweight, or equivalently, that the acceleration of the counterweight is 1/2 the acceleration of the piano. And now we have a third relationship here, which we can use to finally get a system of equations and unknowns that we can solve. And the first thing we should do is we should just get rid of this AC, because it's asking us about the acceleration of the piano. So let's get rid of the acceleration of the counterweight. So we're going to take this top equation there, 2t minus mcg equals 1/2 mc times the acceleration of the piano. And then we can take this second equation, mp g sine of 30 degrees minus tension equals mp acceleration of the piano. Let's go ahead and solve for tension here. Mass of the piano times gravity, sine of 30 degrees minus mass of the piano times the acceleration of the piano is equal to the tension. We can even factor out that mass of the piano. So that's mass of the piano times g sine 30 degrees minus AP. That's our tension. We are going to need a third page here. So let's just take this equation. I'll recopy it up here, that the tension is the mass of the piano times g sine of 30 degrees minus the acceleration of the piano. And then copy over our other equation, this one, that 2t minus mcg equals 1/2 mcap. And we can plug this in for the tension. So twice the mass of the piano times g sine of 30 degrees minus AP minus mass of the counterweight times g is equal to 1/2 mass of the counterweight times the acceleration. And it's the acceleration of the piano that we're looking for, so we're going to have to collect that and expand everything out. So this is going to be, we're going to go ahead and expand this out. 2 mass of the piano times gravity sine of 30 degrees minus 2 mass of the piano acceleration of the piano minus mc times gravity equals 1/2 mass of the counterweight times the acceleration of the piano. We'll collect the piano terms over here on the left, on the right, and we'll collect the other terms on the left. So 2 mass of the piano times gravity sine 30 degrees minus mass of the counterweight times gravity is equal to 1/2 mass of the counterweight times the acceleration of the piano minus or plus twice the mass of the piano times the acceleration of the piano, and factor out the acceleration of the piano. So 1/2 mass of the counterweight plus twice the mass of the piano equals the times the acceleration of the piano equals, well, we can factor out the g, twice the mass of the piano times gravity times the sine of 30 degrees. Whoops, we're factoring out the g. You know what, we'll just leave it there. So this is mass of the or twice the mass of the piano times gravity sine of 30 degrees minus mass of the counterweight times gravity divided by 1/2 mass of the counterweight plus twice the mass of the piano equals the acceleration of the piano. All right, this is admittedly ugly, but you know, this is actually a fairly complicated problem. Let's go ahead and plug in some numbers. So that's twice the mass of our piano is 200 kilograms, 9.8 meters per second squared, and the sine of 30 degrees. Here the mass of the counterweight is 180 kilograms times 9.8 meters per second squared. On the bottom we have 1/2 times 180 kilograms plus 2 times 200 kilograms, and that's the acceleration of our piano. So let's just take each of these terms in kind. So 2 times 200 times 9.8 times the sine of 30 degrees is 1960 kilogram meters per second squared. So newtons minus, we have 180 times 9.8, 1764 newtons. Notice that that subtraction is exactly the tension 2 that we lost when that rope broke. Kind of neat. All right. On the bottom, we have 1/2 times 180 kilograms plus 2 times 200, 2 times 200, which is 400. So this is 490 kilograms. So 1960 minus 1764, that was our 196 newtons on the top and 490 kilograms on the bottom. And so the acceleration is 0.4 meters per second squared. All right, so a bit ugly, but the really important thing to remember is how is it that we related the acceleration of our two moving objects together, and in this case we had to do it by realizing that the rope's length wasn't changing, so that if the piano moved a distance d, the counterweight had to move a distance d over 2. Okay, let's move on to some energy problems. Even more energy problems. All right, so it says, Superman, mass of 107 kilograms, wants to jump over the daily planet, height of 400 meters, in a single bound. With what average force must he push against the ground while leaping if he starts from a crouch with his legs bent and quickly extends them 60 centimeters to their fullest extent? All right. So let's draw ourselves a picture. There's the daily planet. And Superman, it has a height here of 400 meters. And Superman wants to, there he is with his cape, leap over it in a single bound. All right. So height suggests probably some sort of gravitational potential energy is going to be an issue. Indeed, this moment here is an interesting moment. That's the moment when he clears the building. But how does he get there? Well, to get there, he would have to have a certain amount of energy, right? There's a gravitational potential energy up here of his mass of Superman times the gravitational constant times this height. So there's a certain amount of energy he has to have in order to be up there. And the question is, where did that energy come from? So let's think about what's happening down here at the bottom. So Superman crouches and then he leaps into the air. And in doing so, he extends his legs through some distance while pushing. Sorry about that. So much fun teaching and babysitting at the same time. All right, so he has to push against the ground, and as he does so, the ground pushes back on him with an equal and opposite force. So if he's pushing on the ground is pushing on him, and he's moving through a distance of 60 centimeters during the time that the ground is pushing up on him. And so there's a certain amount of work being done which is the force, the average force he's pushing on the ground, times that distance of 60 centimeters. So he pushes with some force F through a distance of 60 centimeters, and that does a certain amount of work, and that's the work that adds energy to get him up there. So if we set this work equal to that energy, so force, average force, times that delta y is going to be mgh, and now we can solve for force, that the average force then he would need to push off with is his mass times g times the height of the building divided by the amount of length that he was pushing through. So that's 107 kilograms, 9.8 meters per second squared, a height of 400 meters, and a displacement here of 60 centimeters, or 0.6 meters. So now we can take 107 kilograms, 9.8 meters per second, 400 meters, divide by 0.6, and that is 7.00 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th newtons, or 700,000 newtons. All right. Leaping tall buildings in a single bound requires some strength. He's Superman. All right, let's try another one. This one says, go ahead and zoom in. An archery bow is drawn 0.5, or a distance d equals 0.59 meters, and loaded with an arrow of mass 0.078 kilograms. The bow acts as a spring with a spring constant of 109 newtons per meter, and the arrow flies with negligible air resistance. To simplify our work, let the gravitational potential energy be 0 at the initial height of the arrow. How fast in meters per second will the arrow be traveling as it leaves the bow? And if the arrow is shot at an angle of 45 degrees above the horizontal, how high in meters above the initial height will the arrow be when it reaches its peak? All right, so let's draw ourselves a picture. And the first moment of interest here is when we've got our bow drawn to full extension. Here's our arrow. We've drawn at a distance here, d of 0.59 meters. And the spring constant here, the spring constant, is 109, little k is 109 newtons per meter. And if this is moment 1, then the energy at moment 1 is all spring potential energy, right? So it's 1/2 our spring constant k times our distance d squared. And the second moment of interest is when our bow has relaxed, our arrow just begins to leave the bow, now moving with some speed v. So this is our moment 2, and the energy at moment 2 is going to be kinetic energy, right? And it's going to be 1/2 times the mass of our arrow times v squared. And because spring potential energy is the only thing going on here, really, then we're just going to equate those two things together. So we can say the energy at moment 1 equals the energy at moment 2, and write down that then 1/2 kd squared has got to be equal to 1/2 mv squared. Now, there's a caveat here, which we're going to that I should introduce, which is that in moving from the stretched position to the unstretched position, technically the arrow has changed altitude a little bit by a 1/4 meter or something like that. So technically the gravitational potential energy has changed slightly. However, compared to the kind of spring potential energy that we're going to get out of it, that change in gravitational potential energy from the relaxed bowstring to the fully drawn bowstring is going to be small enough that it's probably not going to enter the picture at in a meaningful way here. So we're going to go ahead and slightly ignore that tiny little amount of potential energy change that the arrow underwent while being shot by the bow. So we're just going to go ahead and keep this as our equation here. We can cancel the factors of 1/2. We're solving for velocity. So k over m d squared equals v squared, so that our speed is the square root of k over m times d. So that's the square root of 109 newtons per meter divided by our mass of 0.078 kilograms times 0.59 meters. So that's 109 divided by 0.078. Take the square root of that. Whoops. 109 divided by 0.078. Take the square root of that and multiply by 0.59. And our speed is 22 meters per second. All right, so our arrow is moving at 22 meters per second when it leaves the bow. If it's fired at a 45-degree angle, right, so that this is our full V of 22 meters per second, then there is a Vy and a Vx, V naught y and a V naught x, if this is V naught. Technically this becomes a projectile motion problem, and we could solve it like a normal projectile motion problem. We know the angle here is 45 degrees. We know the initial velocity. We can break it up into horizontal and vertical components. We could solve for the highest point, but there's another way that we could approach this problem, and that's the following. Projectile motion, especially projectile motion without air resistance, is another version of a conservative, an energy conservation problem, because the only force at work is gravitational. Gravity is an energy conserving force, it's a conservative force, and so the total mechanical energy of our bow, or of our arrow, must be conserved. We know its initial kinetic energy is going to be whatever the kinetic energy of 22 meters per second is, right? And we know that at its highest point, it will be moving purely horizontally. the velocity at its highest point will be just the horizontal motion, because the vertical motion will have stopped. And indeed, the magnitude there will be 22 meters per second times the cosine of 45 degrees, because that would be what the horizontal component of the initial velocity is. So 22 meters per second times the cosine of 45 degrees, that's 15.6 meters per second. That's the velocity at its highest point, is 15.6 meters per second. And so if this is moment 2, we could call this moment in the air, when it's at some height h, moving at some velocity v high, we can call that moment 3. And indeed, the energy at moment 2 has to equal the energy at moment 3. The energy at moment 2 is r 1/2 mv squared, and the energy at moment 3 is r 1/2 mv high squared plus mgh, the height we are above the ground. And we could cancel out the masses, and we want to solve here for this height. So 1/2 v squared minus 1/2 v high squared equals gh. So h is going to be v squared minus v high squared over 2g. That's 22 meters per second squared, the speed it comes off the bow, minus 15.6 meters per second squared, the speed of just the horizontal component of that initial velocity, divided by 2 times 9.8 meters per second squared. So 22 squared minus 15.6 squared divided by 2 divided by 9.8 is 12.3 meters. So our arrow, 12.3. Our arrow would peak moving at 15.6 meters per second horizontally at an altitude of 12.3 meters above the point that it was shot. And we solved aspects of this projectile motion problem without having to do anything with the projectile motion equations, without having to dig out the kinematic equations or anything. We solved it from a pure energy standpoint by allowing, or by applying some of our knowledge about the way that projectile motion works, and in particular, that the horizontal velocity doesn't change during projectile motion, and that at its peak, the vertical component of velocity will be 0. Okay? All right, let's try another one here. This one says, a bicyclist starting from rest applies a force of 239 newtons to ride his bicycle across flat ground for a distance of 325 meters before encountering a hill making an angle of 24 degrees with respect to the horizontal. The bicycle and rider have a mass of 124 kilograms combined. All right, part one. How much work in joules did the rider do before reaching the hill? Part two. What is the bicycle's speed in meters per second just before the hill? Assume there's no kinetic friction between the bicycle and the ground. And part three here, if the cyclist starts coasting at the bottom of the hill, what distance d in meters does the bike travel up the incline? Okay. So to begin with, we have our bicyclist here. There's a force being applied to that bicyclist of 239 newtons. And that force is being applied over a distance d here of 325 meters. All right, so a force multiplied by this distance, that will give us the work being done, is this force times the distance, and in this case the distance or the displacement and the force are at the same in the same direction, and so the work will just be F times d. So that's 239 newtons applied through 325 meters gives us a work of 239 newtons, 325 meters of 77,000 joules, or 77 kilojoules. Okay, that's the work being done on the bicycle. Now, if the bicycle started at rest, the work here is the change in the energy. That's the final energy minus the initial energy. Well, the final energy is going to be the bicycle is moving at some speed v, it's got kinetic energy. So that's 1/2 mv squared. And our initial energy, well, we started from rest. Sorry, minus 0. Our initial energy is 0. And that's got to be equal to the work. So our final speed then is twice the work divided by m equals v squared, or v equals the square root of twice the work over the mass. So that's 2 times 77,000 joules divided by 124 kilograms, and that gives us a speed here of 626 nope, forgot to take a square root. Speed is 25 meters per second. 600 meters per second. That was going to be an awful lot of speed for a bicycle. All right, 25 meters per second. That's a believable speed for a bicycle. All right, so the bicyclist did 77 kilojoules worth of work. Starting from rest, that brought him to a kinetic energy that gave him a speed of 25 meters per second. To figure out the last part here, how far does the bicyclist travel up the hill? Let's go ahead and draw our picture here. We have an initial speed down here. This is our v initial. We have an angle here of 24 degrees, and we want to know how far up the hill here do we make it. Let's go ahead and give ourselves a new page to work on, and we'll get this out of the way. Well, if we call this here our moment 2 and this our moment 3, again, energy is going to be conserved here between moments 2 and moment 3. So the energy at moment 2 equals the energy at moment 3. At moment 2, the energy is entirely kinetic. That's 1/2 mv squared. And at moment 3, the energy is entirely gravitational potential, mgh, where h is this height above the ground. But we're going to have to, we want to know that length d, not the length h. So we have to relate d to h, and we can do that by saying, again, there's our angle theta. This is our h. That's our d. Opposite over hypotenuse. H over d is the sine of our angle, or d is h over the sine of our angle. But actually we want to get rid of h. So h equals d sine theta, and then we can plug that back in over here. So 1/2 mv squared equals mg times d sine theta. We can cancel the masses and solve for d. So v squared over 2g sine theta is our distance d, and plug in some numbers. 25 meters per second squared on the top, 2 times 9.8 meters per second squared, times the sine of 24 degrees on the bottom. So square of 25, divide by 2, divide by 9.8, divide by the sine of 24 degrees, 79 meters is our distance that we travel up the hill.